Welcome to today's session. In this problem, titled Minimum Space Wasted from Packaging, we will explore an optimization challenge where we aim to minimize the total space wasted when packaging in packages using boxes provided by multiple suppliers. We'll break this down step by step, discussing the approach and key insights to solve it efficiently. Let's dive in. The input consists of two main components, an array called packages that contains the weights of the items to be packaged, and a 2D array called boxes, where each row represents the sizes of boxes available from a specific supplier. Your goal is to determine the minimum total space wasted when using boxes from only one supplier. If it's impossible to package all items using the boxes from any single supplier, you should return -1. The total space wasted is simply the sum of the wasted space for all packages. If no supplier can fit all the packages, you return -1. In this problem, you are tasked with minimizing the space wasted while packaging a set of items. The rules are straightforward. A package can only go into a box if the box size is greater than or equal to the weight of the package, and the wasted space for that package is the difference between the box size and the package weight. To solve this, you must evaluate all suppliers and return the smallest possible total wasted space. The input format includes an array packages, where each element represents the weight of a package, and a 2D array boxes, where each row lists the box sizes available from a specific supplier. The constraints on these inputs are significant. The number of packages can go up to 100,000, and the weights can be as large as 1 billion. Similarly, the number of suppliers and the box sizes they offer can also be quite large, with up to 100,000 boxes per supplier. The output of the problem is a single integer, the minimum total wasted space across all suppliers. If it's impossible to package all the items using any one supplier's boxes, you must return -1. To better understand this, let's look at some examples. In our first example, the packages array is 2, 3, 5, and the boxes array has two suppliers, one offering box sizes 4, 8, and the other offering 2, 8. For supplier 0, we can use box 4 for packages 2 and 3, and box 8 for package 5. This results in wasted spaces of 2, 1, and 3, respectively, for a total of 6. For supplier 1, we use box 2 for package 2, and box 8 for packages 3 and 5. This results in wasted spaces of 0, 5, and 3, respectively, for a total of 8. The minimum total wasted space is thus 6, achieved by supplier 0. This demonstrates how the solution must evaluate each supplier individually and calculate the wasted space for each scenario. In the second example, the packages array is still 2, 3, 5, but the boxes array now has suppliers offering 1, 4, and 2, 3, 8. Supplier 0 cannot package all items, as their largest box, size 4, is too small for package 5. For supplier 1, we can use box 2 for package 2, box 3 for package 3, and box 8 for package 5. This results in wasted spaces of 0, 0, and 3, for a total of 3. However, since supplier 0 cannot fit all the packages, the result for the entire problem is -1. This highlights that even if one supplier can handle the packages efficiently, the solution must ensure that every supplier is considered, and the result is only valid if at least one supplier can handle all the packages. In the third example, the packages are 3, 5, 8, and the boxes array has 3 suppliers with sizes 10, 6, 8, and 3, 6, 9. For supplier 0, we use their single box, size 10, for all packages, resulting in a total wasted space of 14. Supplier 1 uses box 6 for packages 3 and 5, and box 8 for package 8, resulting in a total wasted space of 4. Supplier 2 uses box 3 for package 3, box 6 for package 5, and box 9 for package 8, resulting in a total wasted space of 2. The minimum total wasted space is therefore 2, achieved by supplier 2. This example demonstrates how the solution must determine the optimal allocation of boxes for each supplier and select the supplier with the least wasted space. To summarize, the constraints of this problem require careful consideration of edge cases and efficiency. For example, if all boxes are too small for the largest package, the result must be -1. When there is only one supplier, the solution must ensure that their boxes can accommodate all packages. With input sizes reaching up to 100,000 packages and boxes, the solution must also be optimized for scalability. Additionally, scenarios involving duplicate package weights or diverse box sizes across suppliers must be handled correctly. By addressing these constraints and edge cases, you can ensure that your solution is both accurate and efficient for all input scenarios. To solve this problem, we need to minimize the total space wasted when packaging a set of packages using boxes provided by multiple suppliers. Each package must be placed in a box that is at least as large as the package's weight. The wasted space for a box is simply the difference between the box size and the package's weight. Our objective is to find a single supplier whose boxes result in the least total wasted space. If there's any package that cannot fit into any of the boxes from a supplier, that supplier is not a valid option, and the result in such cases will be -1. To handle this, there are a few key observations. First, sorting is essential because pairing each package with the smallest box that can fit it minimizes wasted space. Sorting both the packages array and each supplier's boxes array helps streamline this pairing process. Second, calculating the total wasted space for a supplier involves summing multiple values. Using prefix sums allows us to compute these sums efficiently in constant time. Finally, we need to ensure feasibility. If a package cannot fit into any box from a supplier, we can immediately exclude that supplier from consideration. These insights lay the groundwork for designing our approach. There are several approaches we can consider to solve this problem. The first is the brute force approach. Here, we check every package against every box from every supplier, calculate the total wasted space for each supplier, and then select the one with the minimum wasted space. However, the complexity of this method is n*m*b, where n is the number of packages, m is the number of suppliers, and b is the average number of boxes per supplier. This makes it infeasible for larger inputs because the number of comparisons grows rapidly. A more efficient solution is the optimized approach, which combines binary search and prefix sums. In this method, we first sort the packages array and each supplier's boxes array. For each supplier, we use binary search to quickly find the smallest box that can fit each package. Then, we use prefix sums to compute the total wasted space for the supplier in O(n) time. This approach involves sorting the packages in O(n) log n, sorting each supplier's boxes in O(b) log b, and performing binary searches for n packages in O(n) log b. The total complexity becomes O(n) log n plus m*, b log b plus n log b, which is far more efficient than brute force. By reducing redundant comparisons and leveraging sorting and binary search, this method handles large inputs effectively. An alternative approach is to use a greedy strategy, where each package is assigned to the smallest possible box without sorting the arrays. This avoids the overhead of sorting but requires the use of a priority queue or heap to keep track of available boxes. While simpler in concept, this approach often becomes less efficient in practice due to the repeated heap operations required for each package. After weighing the options, we chose the optimized approach using binary search and prefix sums as our strategy. This method strikes the right balance between clarity and efficiency. Sorting the packages and boxes upfront simplifies the logic and reduces the computational overhead in the long term. Additionally, prefix sums allow us to quickly compute the total wasted space for each supplier, and binary search enables efficient pairing of packages with boxes. These factors make the optimized approach both scalable and easy to implement, making it the most suitable strategy for solving this problem. When comparing the different approaches, the trade-offs become clear. The brute force method is straightforward but computationally expensive, making it suitable only for very small inputs. The greedy approach avoids sorting but introduces higher overhead due to the need for repeated heap operations, which can make it less efficient and harder to implement correctly. In contrast, the optimized approach is the most efficient for large inputs, leveraging sorting, binary search, and prefix sums to minimize wasted space while maintaining clarity in implementation. Although it requires more preparation upfront, this extra work pays off with significantly better runtime performance. By opting for the optimized approach, we achieve a solution that is both scalable and easy to understand, ensuring that we can handle this problem effectively even for larger datasets. Let's continue. Let's continue. Let's continue. Let's continue. Let's continue. To solve the problem, we start by importing the bisect_right function from Python's bisect module. This will help us efficiently find the position of the smallest box that can fit each package. Inside the solution class, we define the min-wasted space method, which takes two arguments, packages and boxes. The first step is to sort the packages array, which makes it easier to calculate the waste for each supplier's boxes. Next, we calculate the total weight of all packages by summing the packages array. We also initialize min_waste to infinity so that we can track the smallest waste value across all suppliers. Now, for each supplier's list of boxes, we sort the boxes to process them in increasing order of size. If the largest box from the supplier is smaller than the largest package, we skip this supplier since their boxes cannot accommodate all packages. We then initialize variables, waste to track the total space wasted for that supplier, and preb_index to 0, which helps us keep track of the packages we've already covered. Inside the loop over supplier_boxes, we use bisect_right to find the first package that can't fit in the current box size. The number of packages that fit in the current box is determined by the difference between index and preb_index. The space wasted for these packages is calculated as the number of packages multiplied by the current box size, and we add this to waste. We then update preb_index to index, effectively moving to the next group of packages. If preb_index matches the total number of packages, we break out of the loop since all packages have been processed. Finally, we update min_waste to the smallest value between its current value and the calculated waste for this supplier. Once all suppliers have been processed, we check if min_waste is still set to infinity, which would indicate that no supplier could accommodate all packages. In that case, we return -1 as the output. Otherwise, we calculate the result by subtracting the total _package_weight from min_waste to exclude the actual package weights from the total wasted space. The modulo operation with 10**9 plus 7 ensures that the result fits within the constraints of the problem and avoids potential overflow issues. This result is then returned as the minimum space wasted across all suppliers, completing the implementation. Here, we begin the Java implementation by importing necessary libraries and defining the solution class. The function min_wasted_space takes two inputs, an array of packages representing the weights of packages to be shipped, and a 2D array boxes where each row corresponds to the box sizes available from a supplier. First, the packages array is sorted to allow efficient processing. We then calculate the total weight of all packages, which will later help us determine the wasted space. To keep track of the minimum waste across all suppliers, we initialize min_waste to the largest possible value using long_max_value. Next, we iterate through each supplier's box sizes in boxes. For each supplier, we sort their box sizes to ensure the boxes are processed in increasing order. If the largest box available from a supplier is smaller than the heaviest package, it means this supplier cannot handle all the packages, so we skip to the next supplier. For the remaining valid suppliers, we calculate the waste. This is done by iterating through the supplier's box sizes, and for each box size, we determine how many packages can fit using the upperbound function. The waste is then updated based on the number of packages that fit into the current box size, multiplied by the box size itself. We also update preb_index to track the packages that have already been processed. If all packages have been processed, as indicated by preb_index equaling the length of the packages array, we break out of the inner loop to avoid unnecessary computations. After computing the waste for the current supplier, we update min_waste to be the smaller value between the current min_waste and the waste calculated for this supplier. Once all suppliers have been evaluated, we return the result. If no valid supplier was found, indicated by min_waste still being long_max_value, we return -1. Otherwise, we calculate the final result by subtracting the total package weight from the minimum waste and taking the modulus of 1,000,007 to ensure the result fits within the required constraints. The implementation also includes a helper function, upperbound, which performs a binary search to find the smallest index in the packages array where the value exceeds the current box size. This ensures that only packages that fit within the box size are considered for waste calculation. The binary search starts from the given start index to optimize performance, avoiding unnecessary reprocessing of already checked packages. In this example, we start with the packages array 2, 3, 5, and the boxes from two suppliers 4, 8, 2, 8. The first step is to sort the packages array, which is already in sorted order here, is 2, 3, 5. We also calculate the total package weight, which is the sum of all package sizes, giving us 10. Next, we initialize a variable min_waste to infinity, which will help us track the smallest space wasted across all suppliers. Now, we iterate through each supplier's boxes, starting with supplier 1, whose boxes are 4, 8. After sorting these boxes, we confirm that the largest box, 8, is sufficient to fit the largest package, 5. With this condition satisfied, we can proceed with the calculations. Initially, we set waste to 0 and preb_index to 0, indicating that we are at the start of the packages array. For the first box size, 4, we use the bisect_right function to find the index of the first package that exceeds 4. This gives us index equals 2, which means the packages 2, 3 are covered by this box size. Now, we calculate the waste contributed by this box size. The waste is determined by the number of packages covered, multiplied by the box size. For box size 4, this is 2 to 0, asterisk 4 equals 8. We then update the waste to 8 and set preb_index to 2, indicating that we've processed the first 2 packages. For the next box size, 8, we again use bisect_right to find the index of the first package exceeding 8. This gives us index equals 3, meaning the package, 5, is covered. The waste for this box size is 3 to 2, asterisk 8 equals 8. Adding this to the previous waste, the total waste becomes 16. With preb_index updated to 3, we've now processed all packages. For supplier 1, the total waste is calculated as waste total_package_weight equals 16, 10 equals 6. We update min_waste to 6, as it's the smallest waste encountered so far. Next, we consider supplier 2, whose boxes are 2, 8. After sorting, we follow the same process as with supplier 1, calculating waste for each box size. The total waste for supplier 2 comes out to 14, which is higher than the current min_waste. Therefore, we retain min_waste equals 6. For this example, we now have the result. The minimum waste is 6. To return the final answer, we calculate min_waste total_package_weight, percent, 10 to the power of 9 plus 7, which simplifies to 6, as there are no additional mod operations needed. Moving to the second example, here the input is packages equals 5, 8, 10, and boxes equals 4, 6, 3, 7. After sorting the packages, we have 5, 8, 10, and the total package weight is 23. Starting with supplier 1's boxes, 4, 6, we notice that the largest box size, 6, is smaller than the largest package size, 10. Since none of the boxes can fit the largest package, this supplier is skipped entirely. Similarly, for supplier 2's boxes, 3, 7, the largest box size, 7, is still insufficient for the largest package, 10. Therefore, this supplier is also skipped. As no supplier has boxes capable of fitting all the packages, the result for this example is -1, indicating no feasible solution. In the final example, the input is packages equals 2, 3, 5, and boxes equals 5, 10, 4, 6. We apply the same process as in the first example, sorting the packages and iterating through each supplier's boxes to calculate the total waste. After performing the calculations, we find that the minimum waste is 4 for this case. Summarizing the results, example 1 has a minimum waste of 6, example 2 has no feasible solution resulting in -1, and example 3 has a minimum waste of 4. These values represent the final outputs for the given examples. To analyze the time complexity of this algorithm, let's break it into its main steps. First, we sort the packages array in ascending order. Since there are m packages, this sorting step takes m*log m. Next, we process each supplier's boxes array. If there are b suppliers and the ith supplier has k_i box sizes, then sorting their boxes array takes k_i log k_i. After sorting, we perform binary searches for each box size using the bisect_right function to determine where in the packages array the current box fits. Each binary search takes log m time, and since there are k_i box sizes for a supplier, this step requires k_i log m for that supplier. Finally, we update the waste and min_waste values using simple arithmetic, which are constant time O1 operations. When we combine these steps, the overall time complexity becomes clearer. Sorting the packages array contributes O m asterisk log m. Iterating over all suppliers and sorting their boxes arrays contributes O b asterisk k underscore average asterisk log k underscore average, where k underscore average is the average number of box sizes per supplier. Performing binary search for all box sizes across all suppliers adds O b asterisk k underscore average asterisk log em. Adding these terms together, the total time complexity is O m asterisk log m plus b asterisk k underscore average asterisk log k underscore average plus log m. In the worst case, where every supplier has k box sizes, this simplifies further to O m asterisk log m plus b asterisk k asterisk log k plus log m. Now, let's evaluate the space complexity of the algorithm. Sorting the packages array is typically an in-place operation, which means it requires O1 additional space. Similarly, sorting each supplier's boxes array is also an in-place operation, requiring O1 space. Binary search operations only involve traversing the input arrays and do not require any extra space beyond the input. Additionally, we use a few temporary variables like waste, prev underscore index, and min underscore waste, which each require constant space, O1. Since no additional data structures are used and all operations are performed in place, the overall space complexity of the algorithm is O1. Let's compare this optimized approach to a brute force solution. In the naive approach, we would check every possible combination of packages and box sizes, iterating over all suppliers, their boxes, and all packages explicitly. This would result in a time complexity of O b asterisk k asterisk m. In contrast, the optimized approach improves this significantly by leveraging sorting and binary search. Sorting reduces the number of comparisons, while binary search ensures efficient index lookups. This optimization brings the complexity down to O m asterisk log m plus b asterisk k asterisk log k plus log em. Next, we can also analyze the best, average, and worst cases. The best case occurs when all suppliers have only one box size that can fit all packages, reducing the complexity to O m asterisk log m plus b asterisk log m. In the average case, the number of box sizes per supplier, denoted as k underscore average, is moderate, and binary searches are performed for most box sizes. Here, the complexity becomes O m asterisk log m plus b asterisk k underscore average asterisk log k underscore average plus log m. Finally, in the worst case, we deal with many suppliers, each having a large number of box sizes, and all box sizes need to be checked. This results in a complexity of O m asterisk log m plus b asterisk k asterisk log k plus log m. The big O expression is derived by considering the contributions of the sorting steps, which add O m asterisk log m for the packages and O b asterisk k asterisk log k for the boxes, as well as the binary search contributions, which total O b asterisk k asterisk log m. Combining these terms, the dominant factors lead to a final complexity of O m asterisk log m plus b asterisk k asterisk log k plus log m. One of the most common mistakes in this problem is ignoring the need to sort both the packages and the box sizes. Sorting these in ascending order is crucial because it allows you to systematically assign boxes to packages while minimizing wasted space. Without sorting, the solution can quickly become inefficient or incorrect. Another frequent error is using a greedy approach without validating whether the selected box meets the constraints. For instance, you might pick the smallest box, but if it doesn't fully accommodate the package, the solution fails. It's also important to handle scenarios with multiple suppliers efficiently. If you don't pre-compute or combine their box offerings, you might end up with redundant calculations, which inflate the runtime unnecessarily. Finally, overlooking edge cases can lead to serious problems. For example, you might encounter situations where all packages are larger than the biggest box or all boxes are too small for even the smallest package. Testing for these edge cases is essential to avoid runtime errors or incorrect results. Inefficient iteration is another pitfall to watch out for. If you use nested loops to check every package against every box, the result will be an O and asterisk m complexity, which becomes impractical for larger inputs. Instead, you should use binary search to quickly locate the smallest box that fits each package, reducing the runtime significantly. From an interview perspective, this problem is designed to test your ability to combine sorting with binary search effectively. Sorting lays the groundwork, and an optimized selection process shows your ability to handle constraints efficiently. Pre-computing insights, such as prefix sums or minimum box sizes per supplier, can further demonstrate your ability to avoid redundant calculations. You may also be asked to discuss trade-offs between time complexity and memory usage, so it's good to highlight how pre-processing might increase space usage but drastically improve runtime. Lastly, showcasing your awareness of edge cases, such as packages that don't fit any box or duplicate box sizes, can impress interviewers and show your attention to detail. This problem is conceptually related to several others on LeetCode, making it a great opportunity to draw parallels and deepen your understanding. For example, in LeetCode 4.10, split array largest sum, you aim to minimize a maximum value while dividing an array, which is conceptually similar to minimizing space waste here. Another related problem is LeetCode 8.75, Coco eating bananas, where binary search is used to allocate resources efficiently. Similarly, in LeetCode 1011, capacity to ship packages within D days, you focus on minimizing a capacity constraint while partitioning items. Finally, LeetCode 1482, minimum number of days to make M bouquets, involves binary search with constraints on allocation, echoing the need to balance efficiency with problem-specific requirements. These related problems highlight how similar techniques, such as binary search and optimization, can be applied across a range of scenarios. There are several alternative approaches to solving this problem, each with its own trade-offs. The first is a simple greedy approach combined with sorting. Here, you sort both the packages and box sizes, then for each package, select the smallest box that fits. While this method is intuitive and easy to implement, its O(n*(m) time complexity makes it inefficient for larger inputs. A more optimized approach involves binary search. By sorting both packages and boxes, you can use binary search to quickly locate the smallest suitable box for each package, reducing the complexity to O(n*(log)m). This significantly improves performance, but it does require additional pre-processing and careful implementation. Another potential approach is using dynamic programming. With DP, you can minimize space waste by considering subsets of boxes and packages. Although this method is more flexible and can handle complex variations, its time complexity is highly dependent on the state design and can become much slower, making it harder to implement and debug. Each method has strengths and weaknesses, so the best choice depends on the specific requirements and constraints of the problem. Great job! We've explored an efficient way to tackle the minimum space wasted from packaging problem. We covered the key algorithmic strategies, takeaways, and practical applications. Thanks for joining, and don't forget to like, subscribe, and share for more problem-solving insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!